I think that was the Brinch-Hansen shape factors I was using there. But if it does, just correct it now. But it gives you an idea that actually geotechnics isn't that accurate. Nobody can really say which one, whether it's 0.8 or 0.7, to any real degree of confidence. OK, so now we want to put some numbers in that. So we're saying it's equal to 1.2 times Cu, which was 50, times 5.14, plus we've got 1 metre of saturated clay. So the stress at foundation level is 1 times 20, times a shape factor of 1, times a bearing capacity factor of 1. Plus, and the last term is 0 because n gamma is 0. So when I put numbers into that, or when I put it into my calculator, I got 3 to 8.4 kilonewtons per metre squared. So I converted that to a bearing pressure. How do I do that? No ideas? Might try multiplying by the contact area, wouldn't you? So we're saying the ultimate bearing pressure equals, so we'll call it Q ultimate equals 2 times 2 times 3 to 8.4. Do you have a question? Okay. And I got an answer out of that of 14 kilonewtons, which I'm saying is approximately 1.3 meganewtons. So we tend to carry a number of significant figures up until the last line of the analysis, and at that point we say it's geotechnics. We don't know anything that accurately. Oh, I'm sorry, if it's the document camera. If that's the problem, well, firstly, if that's the problem, why didn't somebody say something? Can you read what's written so far, or do you need me to go over it with another pen? OK. Let's see what I can do. Times. Actually, I'm probably better trying to... there. OK. Somewhere about... Is that OK there? Yes. OK. Yes, in the past I'd always work on the overhead projector, but we're trying to keep a record of the lecture so anybody who wants to go back and view it can do. So it's working with the technology and trying to come up with something that works. OK. We've now got to go back to the original problem statement and say, we've now got this moment applied. And we need to work out the effective width. So what we're going to say now is when this load here is being applied, we're going to cut off a bit of the footing so that the load is applied centrally. So if the load is 0.25 metres off centre, that distance there we have to cut off is 0.5 metres. And that makes it a symmetric problem again. Yes, so we're moving the load over by 0.25. So now, if you think about it, that distance there, instead of being 1 metre, is now 0.75 metres, isn't it? So the same amount added to the other side 0.75 makes the overall width 1.5 metres. So the amount you have to cut off is... So in other words, you cut off a piece twice as wide as you've moved the load, because you're trying to make the problem symmetric again, aren't you? So what we're going to say is, well, just for the moment, we'll call it B dash is equal to 2 minus 2 times 0.25 equals 1.5 metres. OK, we need to recalculate the ultimate bearing pressure again. And what we're saying is Q ultimate equals SC times CU NC plus SQ times CU NQ, where because, and we'll put over here, N gamma equals 0, which is why I've left the last term off. Now, what I've done now is just cheat very slightly. I've said when you go from square to slightly rectangular, the shape factor only changes a little bit. After all, when it goes all the way from square all the way to a strip footing, which is an enormously different aspect ratio, it drops from 1.2 down to 1. So going all the way from square to a strip footing, it drops by 0.2. It will drop to about 1.17 or something, but I've ignored that small difference. So I'm saying, for the purposes of the calculation here, I've just said Q ultimate, and let's put an approximate symbol in there now, is approximately 3 to 8.4. So I'm saying the big effect is not in terms of the change in the bearing pressure, but the big effect will come from the change in the bearing area. Now, if we're dealing with a foundation on granular soil, the change in the shape factor in the last one could be more significant, so we'd have to be a little bit more careful there. So I've done a slight approximation. I've ignored the change in the shape factors. So now we've got to say Q ultimate is equal to 2 times 1.5 times 3 to 8.4, and that's equal to 985 kilonewtons. If you like, approximately 1 meganewton. The reduction in ultimate load due to the applied moment, the reduction is 325 kilonewtons. So there's been a 25% drop in the bearing capacity of that footing because of load eccentricity. If that eccentricity if the eccentricity occurs in the worst case loading scenario, then you're going to have to change the design of the foundation. Okay, any questions before we briefly move on? Because yep. Well, I'm hoping, if I've done it correctly, that the reduction minus the other load. Yeah. Simple subtraction. And I pressed the wrong button on that, so that's why it didn't come up. Okay, yeah, it's just simple subtraction, isn't it? Okay, so now let's talk about piled foundations. Now, I make no apology for returning to some of the slides we talked about. We showed a couple of lectures ago. And this is because we need to understand something about method of pile insertion. We're going to have to make design decisions, and those design decisions are going to be based on what happens to the ground as we put the piles in place. So I've got up here, we talk about classifying piles. Lectures on how we classify things can be often very tedious. And that's because it's like giving you a shopping list, saying this is a list of this. This is not what I'm doing. I'm saying we need to know this information because it will determine our design parameters. So we said we've got method of insertion and we've got displacement piles that look like that. So what we're doing with a displacement pile is if we've got the ground surface here, we're pushing the pile into the ground, like so, and the soil around it is being pushed downwards beneath the pile and backwards, like so. So what's happening is the pile is causing a local zone of densification around it, and it's causing a slight increase in the horizontal stress as a result. The other thing we need to know about with driven piles, when we go back to the photograph, is on the scale, on a macro scale, they can be regarded as being fairly smooth. This is a steel pipe pile. We tend to be using, in the UK, really only two materials are commonly used for piles, and they are steel and precast concrete. That's for driven piles, and for cast-in-place piles, it is cast-in-place concrete. So the outside of a precast concrete pile is also relatively smooth. Why do I mention this? Well, we said soils, when they mobilise their strength, may have a peak strength before softening to critical state. We said the difference between the constant volume strength, and I said critical state there. I apologise. If I use the words critical state, just hear the words constant volume. You'll see why I use that phrase occasionally, because in the last part of the course, it's a model called critical state soil mechanics, which explains the behaviour we see. But, OK, so we've got a soil which will mobilise a peak strength and then soften down to a constant volume strength. But that peak strength is associated with the grains having to ride up over one another in order to shear. If we have a relatively smooth surface, we're unlikely to mobilise the entire peak strength. And we might want to design with a reduced value of the peak strength, possibly even the constant volume strength, to avoid over-designing. The other type of pile we have is a displacement pile. So a displacement pile, it's very hard to show the roughness of that hole on a piece of paper because it's rough on, well, let's draw it on the board here. I'll sketch it on the paper for reference later. But the roughness of the hole you'll get from that is literally that sort of level of roughness. Great clods of soil. You can see them being ripped out the ground by the auger. The diameter we use in design for an augered pile is the diameter of the pile itself, because we're guaranteed to have that diameter all the way down the hole, but locally the diameter can be significantly higher. So, what we do with a board pile is before we start, we